Hi, everybody. So we're going to be working with building a confidence interval. And I'm going to begin by saying that a confidence interval is not a probability. It is a length built off of a sample value or a point estimate, and it gives us an idea where the population parameter sits. So there are two that we typically work with. We work with a sample mean when we know the population standard deviation, and what we do here is we're going to use the sample mean as our point estimate. We're going to add and also subtract z sub confidence level multiplied by the population standard deviation divided by the square root of the sample size. Now, this is estimating our population parameter mu. When we only know the sample standard deviation, it's going to look very similar. It has a slightly different multiplier. It's t sub c, comma, degrees of freedom or sample size minus 1, depending on your author. This is often abbreviated degrees of freedom, which is equal to the sample size minus 1, so that's why they're interchangeable, and then multiplied by the sample standard deviation divided by the square root of the sample size. There are times when your author will use this top formula, and it will say, well, we have a good estimate with the sample standard deviation, and we'll plug that in there. I tend to follow it a little bit more formally and use the t-distribution at that point in time. So we need to address what these multipliers are, but let me finish this piece up here. This is also estimating where the population parameter is. And when we're dealing with a proportion where we get an x and an n, we get a p hat, and then we do a plus or minus a z sub c. And this z sub c is the same as the z sub c above, and then it's multiplied by the square root of p hat q hat divided by n. And there are things that you have to have happen for this to work. Your n multiplied by p hat and your n multiplied by your q hat are both supposed to be greater than or equal to. Now, let me point something out here. Depending on the author, it depends on the value. I learned it as 5. I believe your author uses 10. And I've actually seen authors use 15 in the past, but we will go with NP hat and NQ hat have to be larger than 10. And then it's okay to approach it with this confidence interval formula. So let's address what this z sub c and this t sub c and this z sub c is. It's a multiplier, and it is built off of the normal distribution or the t-distribution. So understand the t-distribution is the normal distribution baby. So as your degrees of freedom, as your sample size gets bigger, your t-distribution becomes more and more normal as it grows. So if your confidence level is 95%, and this is the default level for confidence intervals. So the default level for hypothesis testing is alpha, and it is 0.05 if nothing is mentioned. Well, the default level for confidence intervals is 95% or 0.95. And the thing that you can recognize is that the confidence level plus alpha is equal to 1 if it is a two-tailed test. If it's a one-tailed test, then it's the confidence level plus 2 alpha is equal to 1, okay? You can ask about that if you want to. It will become more apparent as we do hypothesis testing. So let me just clean this bit up here, and we'll get there, and we'll go there. So what's happening is that when we talk about the confidence interval, and this is where the probability gets, like, people think it's a probability, but it is not. It is a distance. And what we're doing when we're talking about the 95% confidence interval is we're pinning the middle of the normal curve to have 95% of the area. Well, that's going to leave out in the tail 0.025 as well as 0.025. Now, to get this value, if it is a z, if we know the standard deviation of the population, we use INV norm, and our area that we use is 0.025, and you're going to leave the mean 0, and you're going to leave the standard deviation 1, and what you're going to get out of there is a negative 1.96. So this is the multiplier that will go here. It is also the same multiplier that will go in this spot here where it says z sub c. Now, if this was the 90% confidence interval, what would happen is on the left you'd have 0.05, and on the right you'd have 0.05. Well, in the left-tailed test, or in the left tail, you'd say it's 0.05, and then you do your INV norm, and that just looks terrible, so I'm going to erase it and rewrite it. So INV norm, and then you're going to use 0.05 as the area, and then the mean is 0 and the standard deviation is 1, and you're going to get a negative 1.645. So it's helpful to draw this little sketch, and this negative 1.645 is the value that goes here in that z sub c. It would be written z sub 95. Now, I have to be careful there because I think your author at times will write it as, oh, you're supposed to think about it as z sub 0.025 because 0.025 is in the left tail. So just be aware that it may write it that way. I think it does. Now, what if it's a t-distribution? What if they give you the sample standard deviation rather than the population standard deviation? Well, it's done basically the same way, except instead of using INV norm, you're going to use INV, and then you're going to use t. And then you use the area of 0.05, and then your degrees of freedom determine the shape of your distribution. So if your n, your sample size, was 20, you would put 19 in here for your degrees of freedom. Now, not every calculator has INVT. It's, second var is INV norm, second var is INVT, but INVT isn't always there if it's an older calculator. So you have to use a table. So to do that, you've got to get a t-distribution table. Now, you can call them up pretty much anywhere. Let me do some cleaning up here so we can see this. And again, we're going to think about it from the perspective of two components. Component one is what is our area in the tail. So if our area in the tail is 0.025, we're up here. See the 0.025. And again, we draw it, but if our area in the tail is 0.05, we go to this spot, the 0.05. And then our degrees of freedom is the sample size minus 1. So we just traveled down to, and I said 19 because that's our degrees of freedom. And so we would travel over here and we'd say, oh, there's our critical value. It's 1.729. And the value that gets used in this piece of the formula is 1.729. Now, let's do some just brief examples. I am going to make a comment as I'm trying to type some stuff up and erase things. The confidence interval, you need to think about it in this perspective. If you were to do 100 samples, you would have 100, most likely 100 different sample means or 100 different sample proportions. And then building off of that, you work to the left and you work to the right using these multipliers and the values that you're given. Where people get sort of this, another place where people get confused in terms of this idea of its probability is the following statement. And this is a correct statement, but it is not, it's a little confusing, so just bear with. If you were to do 100 samples, and you got 100 different sample means, which is most likely the case, and you found the what is referred to as the margin of error, and I will circle this. This piece here is the margin of error. This piece here is the margin of error. This piece here is the margin of error. So there are 3 margin of error formulas, depending on which thing you're trying to approximate. Oop, I did forget to say that we're trying to approximate the population proportion here. But margin of error, margin of error, margin of error. And once you use that margin of error to find your confidence interval, you will have 100 different confidence intervals, and they'll be slightly different from each other. And this is the phraseology that's used. It works out that about, if you're doing the 95% confidence interval, about 95 of them would contain the actual population proportion value. And what that means is that you might have 90 of them, you might have 85 of them contain it, you might have 99 of them, you might have all 100 of them contain the population parameter, but it's somewhere around 95 out of the 100. So you have to keep that in mind, that about is in there. All right, so let's just do some numerical example stuff here. So suppose we get a sample mean, and our sample mean is 28. I'm just pulling numbers out of the air, but I'm just trying to give you an idea of how it fits together. And we are told that the population standard deviation, and I'm going to make it decent to work with, is 36. And our sample size is going to also be 36. Whoops, typo. I don't want that to be, I want my n to be 36. So let's change this to 6, and let's do this to be 36. There we go. Now, if you are not told what confidence level to use, you automatically use the 95% confidence interval. That's an automatic. Okay, well, here's what we do. We figure out our INV norm, and it'll be 0.025, because we did that earlier, and we're going to have negative 1.96 as our multiplier. Well, what's going to happen is you're going to take 28, that's our x bar, and then you're going to have plus or minus, and it'll be 1.96. Now, you might ask the question, well, what happened to the negative? Well, the formula already has built into the fact that it's got the plus and the minus. It considers when we put that 95 in the middle, here's our 95, that we actually generate a negative critical value as well as a positive critical value, and the formula already has that built into it. So all we need is the numerical value, the 1.96. Now, I'll clean this up a little bit. The next piece we're going to do is we're going to multiply by the population standard deviation divided by the square root of the sample size. And what's going to happen is you're going to have 21, I'm sorry, where did 21 come from? 28, forgive me. 28, and then it'll be plus 1.96. Now, the square root of 36 is 6, and so 6 divided by 6 is 1, and so we're really multiplying here by 1, so we just 28 plus 1.96. And then the left side is 28 minus 1.96. And that's our confidence interval. Now, you can do this on your graphing calculator as well. If you hit the stat key and then you arrow over to tests, and you look for, you got to find Z interval. It's number 7. And it's going to say data or stats. And you're going to hit stats because we're typing in the stats. And our population standard deviation is 6. Our sample mean is 28. Our N is 36. And it says sea level. It's already set to 95. You might have to change it because somebody might have used your calculator or you bumped something, but then you hit calculate and you're going to get 24.06 and 29.96 for the Z interval. All right. Now suppose this changes a little bit and instead we're dealing with, instead of the population standard deviation, we are dealing with the sample standard deviation. Well, there'll be some things that change. Let me erase this stuff, because what we're dealing with now is the formula below where we have the sample standard deviation in place. This doesn't change, this part doesn't change, but our multiplier does change. So we've got to find T sub 95 with degrees of freedom of 35. The sample size stays there, the standard deviation stays there, but what we need here is a different multiplier. So the table that I provided up here doesn't go down to 35 for the degrees of freedom. You can find them online. There's one in our textbook, so they're available. You just got to go to tables. So stats, oops, I'm sorry, I screwed up. So we need to do second vars, and we got to go to INVT. The area is going to be 0.025 because we're dealing with a 95% confidence interval, and 95 is in the middle, and 5% is shared within the two tails. Our degrees of freedom are 35, and our multiplier will be 2.03. So what we're going to have here is a 2.03. Now, again, you can do this on your calculator, but it is T interval instead of Z interval. So Z for this thing, and then T for this one. So you do stats button, you go down to tests, and you find number 8, which is T interval. You hit enter on stats, and your sample standard deviation is going to be 6. Your confidence level, again, I'm leaving it at 95, but go ahead and hit calculate. It takes a second, but you're going to be at 25.97. And then 30.03. Now, the proportion one takes, let me back up for a second. We say we are 95% confident that the population parameter mu is between these two values. And that's the wording of it. Again, not a probability. All right, so let me clean this up a little bit, and then we're going to do a proportion one. Let me show you how that works. And generally what happens is the problem looks very bare. When you read it, all you need are two things. So you need an x value and you need an n value. And the x value would be like, the way they say this is the following. So you have 28 is the number of successes, for instance, and your n is equal to, I don't know, let's say 56. We're going to make our lives nice that way. So our p hat is 28 divided by 56, and then our q hat And by the way, this equals 0.5. And so our q hat is 0.5. And what we have to do is we have to multiply 56 times 0.5 and 56 times 0.5 and see if those are both larger than 10. And they will be in this instance. I set it up to be able to do that. So you should show np hat and nq hat, and that they are both equal to 28. And then you are good to proceed with the confidence interval. So our p hat is 0.5. We've got that there. So what we do is we go 0.5, and then we have plus or minus, and so it's z sub c. And if we do the 95% confidence interval again, we're going to get 1.96 multiplied by the square root of p hat, which is 0.5, multiplied by q hat, which is also 0.5, divided by n, which will have 56 there. Okay, again, you can do this on the handy-dandy graphing calculator. So you're going to hit the stat key, you're going to go to tests, and you're going to find one prop z test. It's number 5. And you're going to hit enter. Oops, not z test, z int. I am wrong. So stat, go to tests, z int, one prop z int. There it is. It's letter A, not test. Whew. I'm sorry for that, folks. So it's going to ask for your x, which is 28. It's going to ask for your n, which is 56. It's going to ask for your confidence level. It's going to take care of all the other formula stuff. You hit calculate, and your proportion, the population proportion, is somewhere between, or we are 95% confident that it is between 0.36904 and 0.63096. All right. Hopefully that helps in terms of the process of building one. All right. Have a good one.